and welcome to the second session on binder performance and testing. Let me introduce myself. I'm Jean-Nicolas Després, working for Shell Bitumen and based in France. I'm currently Senior Application Specialist for France and Benelux, and from 1st of August of this year, I will become the Regional Technology Manager for Europe, taking over from Beer. First, I would like to thank you all for joining this session, but above that, I would like to sincerely thank all presenters for having carried out such a great work in preparing and recording these presentations. I'm very excited to host this session, and I'm sure that you are as excited as me, given the very interesting topic which will be presented today. The beauty of bitumen and of technology is that even if bitumen is known and used extensively for decades, thanks to people like Ian, Marita, Jan, Muhammad, Pavel, Gerald, and Shaheen, and thanks to their teams as well, we are still learning and discovering ways to improve the performance of our products and the durability of our roads. The result of this work fits also very well in the current environment where sustainability of our products is of utmost importance. Let me now share with you the program. This session will be split in 2 subsessions. Each subsession will be made of 3 presentations. At the end of the presentation, you will have the opportunity to ask questions to our presenters or their representative during 10 minutes. I will be the facilitator for this session. To ask your questions, please use the Q&A chat box. You will also have the possibility to vote for the questions which have been already asked. In order to facilitate my task, can you please start your question with the name of the person to whom you would like to ask this question? Thank you for your understanding. It's now time to start. Let me introduce your first presenter, Ian Lancaster. Certainly a lot of you already know Ian. Ian is a UK technical manager for Ninas Bitumen and has worked for Ninas for 27 years. You may know Ian for his engagement in Eurobitume, where he is the chair of the Eurobitume Test Methods Task Force, and where he is also part of other technical committees. You may also know him for his engagement in Energy Institute, where he is the chair of the Bitumen Test Methods Expert Panel. Based on all this experience, Ian prepared a very interesting presentation where we'll cover the effect of sample preparation techniques on the observed morphology of polymer-modified binders and explore the relationship between this and storage stability.
Good afternoon, everybody. It's a pleasure to be speaking at this first Eurobitume Asphalt Virtual Congress and the 7th Eurobitume Asphalt Congress in total. I'm today going to talk about the effect of sample preparation on the morphology of polymer modified bitumen by fluorescence and optical microscopy and its relation to storage stability. I've always had an interest in microscopy. My focus has been on polymer modified bitumens pretty much throughout my career. This study has 2 primary aims: to study the effect of sample preparation on the observed morphology of PMBs, and to determine if there is any correlation between morphology and storage stability as revealed using EN 13399. Another aim of that was to look at the practicality of preparation techniques. I'm a big supporter of making preparation techniques and making bitumen analytical techniques as easy and practical as they possibly can be. In the study, we looked at 3 different binders: a propane deasphalted bitumen of North Sea origin, a visbroken residue of Urals origin, and a South American straight run bitumen. We looked at 4 polymers, 3 SBS type, a high molecular weight radial SBS, a medium molecular weight linear SBS, and a high vinyl medium molecular weight SBS, and also 1 ethylene vinyl acetate of melt flow index of 20 and 20% vinyl acetate. We had 5 different preparative techniques, which I'll cover in the next slide, and 2 different observation techniques using UV reflection and white light transmission. So in total, we looked at 60 binder samples and 2 observation techniques. The preparation techniques, starting with EN 13632, which requires us to place a molten sample of bitumen into a dish which is held in a heated sand bath. We then remove the sand bath and allow the sample to cool to ambient temperature, cool it still further down to -20 degrees, and then remove a sample by fracturing, and that's then applied to a microscope slide. There are 3 what I call direct application techniques, the first of which is what we call the spot technique. This allows us to place a spot of molten bitumen using a heated glass rod onto a cold microscope slide. The spot annealed technique, which involves taking that spot of bitumen onto a microscope slide and then heating it until it flows out and covers the boundaries of the cover glass, and a hot casting technique, in which we place a molten drop of bitumen onto a heated microscope slide, then cool it and observe it. And finally, the fracture surface technique, which involves preparing a shortened BBR mold, cooling that down to -8, in the first instance to -18 degrees in a freezer, then to -24 degrees in a BBR bath, and fracturing the surface, then applying it to a microscope slide. This gives us an overview of the binders that were assessed. Our aim was to produce a nominal 100 penetration bitumen in all cases, use identical preparation techniques for the PMB samples, and look at the physical properties, but with a particular focus on storage stability. This is what the study was all about. There are 3 binder samples there which stand out as being grossly unstable. Those are CCC SBS R here, CCC SBS L here, and AAA SBS R. So what do we observe in terms of microscopy? The study is too large to reveal all of the images that we have, and the time is not long enough for me to reveal all slides. So I'm just going to focus on 2 samples. The first is bitumen AAA, which is our deasphalted bitumen. And looking at this first slide, the difference between the linear and the high molecular weight radial. I would draw your attention to the effect of the different preparation techniques on the observed polymer morphology. Here and here, we see the effect, the morphology obtained using EN 13632. In both cases, that morphology is rather coarse and could lead to an indication of instability. Here and here, we see the morphology obtained using the fracture surface technique. And again, this gives an indication, a potential indication, that that polymer modified bitumen would be unstable. However, if we look at the direct application techniques, which is here spot technique, here spot annealed, and here the direct casting technique, in the case of our stable binder, SBSL, we see very, very subtle, if any, changes in the morphology. Whereas with our unstable binder, SBSR, we see quite significant changes between those three direct application techniques. This indicates that when we apply a secondary source of heat, particularly in the case of SBSR, we see a change in the morphology, which is a potential indication of instability. The final sample here is a white light transmission sample, and it goes to indicate the size of the polymer domains in that unstable sample. In this case, we look at the high vinyl sample polymer compared to the radial high molecular weight polymer in our Urals Visbreaker residue. Here we have a stable and a semi-stable binder. The results, though, are really rather similar. In both cases, we get a coarse dispersion in our standard preparation technique, EN13632, and also the fracture surface technique. However, again, the direct application technique, spot annealed, and hot casting show very little changes in the case of the stable binder and subtle changes only in the case of the semi-stable binder. So this gives us evidence that those direct application techniques are a potential indicator of storage stability. So in conclusion, we can conclude that sample preparation has a significant effect on the morphology observed in a PMB. EN13632 and the fracture surface give coarse, space-separated surfaces, both difficult to observe, neither of which gives a correlation with EN13399. The direct application techniques, however, indicate that the morphology depends upon composition, gives excellent correlation with 13399. Sample preparation is both rapid, simple, and effective. The surface is easy to observe and allows the use of white light illumination.
Thank you, Jan, for this presentation. Now, let me introduce to you Marita Turk. Marita is a member of the Slovenian Chamber of Civil Engineers, working in the field of geotechnics and asphalt. Over the last 10 years, Marita is the head of Laboratory for Asphalt and Bitumen-based product at ZAG in Slovenia. In this role, she's taking care of research work in the field of asphalt and bitumens, quality control for third parties, as well as investigation of non-conformities encountered during the execution of paving jobs. Today, Marita will present the result of extensive testing being done on several samples of 458065 PMB, done to determine the impact of aging on bitumen.
Dear ladies and gentlemen, I'm going to speak about the rheological characterization and comparison of aged polymer modified bitumens. My colleagues Marian Tušar and Lydia Eržek, we all work in ZAG Laboratory for Asphalt and Bitumens in Ljubljana. For heavily trafficked road in Slovenia, we use PMB 458065. In our lab, we do traditional tests as well as rheological tests. But unfortunately, we don't have indicative values what the results of these rheological tests should be. This is why we decided to test it more PMBs. In our laboratory, we do mostly third-party control for motorway maintenance network, So From this job, we get asphalt mixes, asphalt scores, and also bitumen that is delivered to asphalt plants. So we test original bitumens, we test RTFOT-H bitumens and long-term H bitumens, as well as we recover bitumen from asphalt mixes and test recovered bitumen. So we took 5 different samples of PMB from different producers, and we took samples at asphalt plants, and they mixed these bitumens into SMA, asphalt mixtures, and we actually also took these 4 of them for asphalt SMA mixtures and tested the recovered bitumen. Slovenia is a small country, but it is morphologically very diverse. We have hot Mediterranean climate at the coastal area, we have cold in the Alps, and we have cold winters and hot summers in the Pannonian Plain. This is why our asphalts should withstand low temperatures as well as high temperatures. In our national specifications, there are a lot of reference values for traditional tests for bitumens. In our lab, we also do DSR testings to determine complex shear modulus and phase angle, and we also perform the BBR testing, the bending beam remometer test. So we are able to do these tests, but we don't have indicative values for results of these tests. We do short-term aging with rolling thin film oven test, and we also age our bitumens in pressure aging vessel. Here are the results of 5 different samples of PMBs, and the blue color illustrates the original bitumens, the gray color illustrates the RTFOT-H bitumens, and the black color long-term H bitumens. From the penetration graph, we can see that all bitumens got stiffer with aging, which is actually expected. And we also did DSR testing, and we plotted the temperature at which the complex modulus is 15 kilopascals. We can see also from this graph that all bitumens got stiffer with aging. But we can also see that the difference is quite big after long-term ages. This is RTFOT and PAV. At that temperature, we also plotted the phase angle. And we can see that phase angle gets lower with aging. And from this graph, we can see that the differences in bitumens are quite big because the bitumens ages differently. This is the graph with the result of ring and ball tests. We can see that softening point mostly gets lower with aging, but not in all cases. So we think that softening point test is not very appropriate test for characterization of PMBs. These are the results of DSR temperature sweep test for sample number 3. On this side are results of laboratory H bitumens. This is regional RTFOT-H complex models and long-term H bitumen, and these are the phase angles. And here are the results of laboratory aged and recovered bitumens. So this is the comparison of laboratory aged and naturally aged bitumen. You can see that the matching of these 2 bitumens is quite good for the complex modulus and also for the phase angle. We also aged them with PAV, and the comparison is not so good, but it's relatively good. Actually, with sample number 3, we got the best matching with laboratory aged and with naturally aged bitumens. These are the results for sample number 4, laboratory aging and comparison of laboratory aged and recovered bitumen. In this case, we didn't get so good matching. And this bitumen is actually a little bit stiffer than sample number 3. Here we see DSR tests, results of DSR tests performed according to two standardized EN methods. All our tests were performed in ZAC laboratory with the same staff and according to EN standards. For DSR tests, we always use two parallel samples, and you can see that repeatability of the results is very good. So for sample number 5, RTFOT aged, we determined the temperature at which complex modulus is 15 kilopascals, and we determined the corresponding phase angle, which is here. And we plotted this on this graph. This is the point here. So for all bitumens and original RTFOT aged and long-term age, we plotted these values for all 5 bitumens. And actually, we can draw a linear line through 3 points of the same bitumen. So the bitumens have very distinguished way to when we age them. But we can see the big difference with the PMBs of the same time, but from the same producers. We have to know what are the characteristics at low temperatures of our bitumen. So we age bitumens in our lab, long-term aging, and then we tested them. We did the frost test and the bending beam rheometer test to determine limit stiffness temperature and limit M-value temperature. And from all these results, we can see that actually all 5 bitumens behave very good at low temperatures. We did test just these 5 bitumens, but also other bitumens. So in this graph are results of 11 samples of the same type PMB made by 7 producers. Here are the results of frost temperature, and this is the limited stiffness temperature and limited M-value temperature that we get from the BBR tests. We can see the correlation between these values, and we think that this correlation is quite good because frost method is not very exact. So to conclude, characteristics of PMB which are delivered to asphalt plants can be checked quickly with rheological tests. 2 rheological tests, DSR temperature sweep and creep and recovery tests, they offer very good characterization. And they're quite quick, but we don't have any indicative values for the results of these 2 tests yet. Not enough, at least we have some, but not very many. Laboratory aging of bitumens takes a lot of time, skills, and equipment. For laboratories like ours, which we do the quality control of asphalt mixes, it is important to be able to compare the characteristic of recovered PMBs and laboratory age PMBs. We tried to compare several samples, and in some cases we got good correlation, and in some cases we didn't get good correlations. So thank you very much for your attention.
Thank you, Marita, for this presentation. So to complete the first session, I would like to introduce you Jan Su and Muhammad Muadsen. Jan holds a Master of Science in Material and Chemistry and specializes in energy and product at IFP School. She's working for Total as a research engineer in the research center of Solez. Muhammad is also working for Total. He started also his career in the research center of Solez, where he developed and formulated new bitumen for road and industrial applications. Since 2017, he joined the bitumen direction at Paris as a product manager and is in charge of the portfolio of Stirelf PMBs and industrial bitumen. He is also the author of numerous scientific publications regarding bitumen and produce more than 15 patents or patents application. The presentation will be done by Jan, and Muhammad will take part to a Q&A session. During this presentation, Jan will bring us through the work carried out to develop a methodology used to evaluate the oxidative aging resistance of bitumen binders.
Hello everyone, this is Jeanne Zhu from Total Marketing and Services. I'd like to thank Euroasphalt and Eurobitume for giving me this opportunity to present you our work on a methodology to evaluate oxidative aging resistance of bitumen binders. I'd like to acknowledge my co-authors, Mohamed Moazen, Laurence Lapalu, and Zanke Schroeder. What motivated our work is that we know roads age with time due to environmental conditions, resulting in changes in asphalt properties. We know also that their maintenance is costly, so the less the communities have to maintain or replace their roads, the better. Now, if we look at the damage causes, there are multi-factor and multi-scale, as you can see here. And when studying aging topic, it is important to consider the three scales: binder, asphalt mix, and pavement. It is also important to look at several parameters in parallel. And in our work, we have focused on oxidation as it is the main factor of aging. Thus, the objectives of our work were to develop a binder less sensitive to oxidation, which will have a longer longevity on roads in order to reduce maintenance and/or replacement cost and emissions. And for that, we also aimed at developing a screening method to assess oxidative aging kinetics of a binder. For that, we have applied multi-PAV aging, which in fact is the standard PAV aging at 100 degrees Celsius and 21 bar. But instead of 20 hours of time, we have extended it to 25 hours, 48 hours, and 72 hours. In addition to those three aging levels, we have also considered the unaged status, which is called T0. And for the four aging levels, we have characterized the binder and looked at the empirical, chemical, and physical properties. For each test method, we have done some statistical analysis, including the aging step, to enable us to evaluate how much difference, how much variation between two binders is significant. And for the chemical and physical properties, we have plotted their evolution with PAV durations, and we have compared the normalized slope calculated using the equation at the bottom of the slide. And we have plotted then the values in a spider chart in order to ease the comparison between several binders. And in addition to those properties, we have also plotted the normalized delta softening point, where delta softening point was calculated as the softening point at 72 hours of PAV minus the softening point at T0. In this study, we have characterized three 3550 NIT bitumen coming from three different refineries, which means that they are coming from also three different crudes. And they are named binder A, binder B, and C. We have also characterized two special bitumen, binder D and binder E. And in this work, we have taken binder A as a reference. So if we look at the comparison between the three virgin binders. You can see here the spider charts with the details in the paper. And if you look at the spider charts, the wider the area of the spider chart of one binder, the less it is sensitive to oxidation. So if we look at those results, binder B is better than binder A and C. And we can say that sensitivity to oxidation depends on the binder origin, which means its refining process and or its crude. The other important point to have in mind is that if you want to compare the effect of two additives, we need to compare them using the same bitumen base. Otherwise, we can only compare the whole formulation performance. Now, if you look at the special bitumen, with a focus on the black space first, binder E shows different rheological footprint even at T0 compared to binder A. And if you look at the evolution with aging, where phase angle will decrease and the complex modulus will increase, which means that we expect to go from top left to bottom right, we can see that binder E shows narrower change in those two parameters over aging compared to binder A. And if we compare binder binder D, we also see less evolution compared to binder A. Now, if you look at the low temperature properties by performing DBR test, we observe that binder E shows lower critical TS and TM temperatures compared to the two other binders. When we look at delta TC and its evolution with aging, we expect that delta TC becomes more negative, and we can observe that there is a slower evolution for special bitumen and especially binder E. Now, if we look at the final comparison, the multi-factor comparison, we can see indeed that binder E shows a wider spider chart, which means that it is less sensitive to oxidation compared to binder D and binder A. To conclude, we were able to develop a methodology to assess the oxidative aging kinetics of binders, and we were able to differentiate all the formulations studied here. Neat bitumen of the same grade show different sensitivity to aging depending on its origin, meaning refining process or crude. The two special bitumen showed better resistance to oxidation compared to the three neat bitumen. Of course, our methodology is still improvable. For example, if we want to assess the polymer modified binders, we need to add some elasticity parameters. And here we have only considered oxidative aging. And further work is still needed to develop binders for a more durable road. As said at the beginning, when studying aging topic, we need to also evaluate at asphalt mix and road level. We need also to consider the effect of RAP on resistance to aging. We need to assess the recyclability of special bitumen, as if they are on the pavement, they will be also reclaimed and recycled. And we need to understand more aging mechanism. And last but not least, we need to work on the prediction of service lifetime. Thank you for listening to this presentation. There are more details in the paper if you are interested. And we are now pleased to answer to your questions and hear your feedback.
Thank you, Jen, for this presentation. We will now move to Q&A session. We will have 10 minutes to cover the questions you already asked on the application. And we will start. So I will just ask, I think Jan is also online. That's perfect. So let's start with the first question, which will be a question for Jan. Jan, is there a relation between microscopic phase separation and cooling speed?
Yeah, quite probably. In the study, if you look at what we did, the standard method EN 13632, 642, sorry, the cooling rate there, we go from say 160 degrees down to ambient temperature in a period of around about 1 hour. And that tended to give us the most coarse dispersions. And the next level of cooling was in our modified BBR, the fracture surface technique. Cooling was achieved really within about 15 to 20 minutes, and the most rapid is with our spot technique. So yeah, there is probably a relationship there between the rate of cooling and the morphology that's observed.
Great. Thank you for your answer. The next question will be for Mohammad. Mohammad, did you also measure SARA analysis of the best bitumen to compare difference in composition?
Yes, we did. We measure, in fact, the different the SARA composition for the three bitumen used in this study, and we compare before and after aging, and we try, in fact, to establish some relation between aging, oxidative aging, and the modification or the composition of SAR. So if you need more explanation or more details, you can contact me, or we can share with you, in fact, our results on the page.
Great, thank you, Mohammad. The following question will be for you, Marita. The question is, did you take into account the effect of the methylene and aging during the extraction process? And how do you think this influenced the results? Can you compare, in fact, recovered bitumen with fresh bitumen?
Yes, of course. The mixing process and aging during mixes was not the same for all the asphalt samples, because they were produced at different asphalt plants with different producers and so on. But we did the extraction process in our lab with the same operator, and also the distillation person was made by the same distillation. So in a way, this is comparable, but the aging at asphalt plant is not the same. And of course, this procedure affects the aging of the bitumen, but it affects them all the same because it was the same procedure. Maybe the PMBs are not of the same constitution, so they're a little bit, this process influences them differently, but in general, this is what we get. This is the best what we can get from asphalt mixes. There's nothing else we can get. So if this answers your question.
Yeah, that's good. Thank you. Thank you, Marita. Jan, another question for you. If a crosslinker would have been used, do you expect the same quality of image and ability to identify stable or unstable blends? And depending on based on your findings, do you expect any changes? That's the second question, but it's still part of the same. Do you expect any changes on the EN standards based on your findings?
If I can take the second part of that question first, I hope there will be some changes with the EN standard. I find it quite it's very time consuming, and it's relatively complicated, and it produces surfaces which are particularly difficult to observe under the microscope. With the question regarding cross-linking, yes, I would expect similar sort of observation, and I can the technique can be used to indicate when the cross-linking hasn't actually worked. So with a genuinely well-dispersed, well-cross-linked system, first thing that happens is that the surface is very difficult to observe. It's a very indistinct boundary between the phases, so it can be quite difficult to observe. But if we pass that through the spot and the spot anneal technique, and also the hot casting technique, if the cross-linking hasn't worked, then we will still see those differences. And they can still be related to storage stability.
Okay, thanks. Good. Thank you for the answer. Following question will be for you, Mohamed. Was the aging resistance of the different binders validated by testing of the asphalt mixes?
Yes, in fact, it's in progress. In fact, we to answer to the question, we work on two levels. The first one at lab level, where we tested the 5 binders in asphalt mix, where we compare in fact to the fatigue level the 5 binder, and also by comparing binder A, B, C, and E on road construction. In fact, we started in 2019. We have different sites, and the objective, in fact, is to monitor this sites and to get sample after 1, 2, and 5 years in order to correlate the results or the evolution of results between lab at binder scale, lab at asphalt mix scales, and road on asphalt mix. So it's in progress.
Great, thank you, Mohamed. Another question for you, Marita. Are there any other rheological test methods that you would recommend other than BBR and DSR?
Actually, on extracted bitumens, we do a lot of creep and recovery tests, multiple stress creep and recovery tests, and we do a lot of DSR tests because one needs a very little amount of bitumen for these tests. We don't do so much BBR tests because it's time consuming and one needs a lot of bitumen. So I would recommend the multiple stress creep and recovery test for extracted bitumens to get a feeling of how elastic is the sample, and also the DSR tests.
Okay, good. Thank you, Marita. One more question for you, Jan. Do you believe that a tube test is a good test to test the storage stability of PMBs, and does it really reflect the practice?
It's adequate. It's certainly not the best method for assessing storage stability. If we look at what happens, we place hot bitumen into the tube, we allow it to cool down, we seal it, we then place it back, it warms up again, we take it out of the oven, we cool it down and we section it. So we introduce a number of thermal stages which are not relevant to what happens on an asphalt plant. I know we're short of time. My preference for measuring storage stability is using a hot tube with drains on it. It's much more relevant to what actually happens in a storage tank out on a site.
Okay. Thank you, Jan. Thank you everybody for this first session. Very interesting presentation, and thanks a lot for all your answers. Let's now move to the next 3 presentations. So to start, let me introduce Pavel Chris. Pavel has about 20 years of asphalt technology experience, ranging from material characterization to asphalt production and customer support, during which he wrote over 30 technical papers and several patents. He currently leads the American Asphalt Technical Organization for Imperial Oil and ExxonMobil companies in Sarnia, Ontario. Pavel is also involved in Asphalt Institute, where he chairs the Technical Advisory Committee, as well as in the Transportation Research Board, where he is a member of the Production and Use of Asphalt Committee. Today, Pavel will bring us through the work he did to study the ability of the SuperPave specification test to identify phase instable or incompatible bitumen.
Hello, this is Pavel Chris, and today I would like to talk about rheological properties and how they can be useful in identifying phase incompatible bitumen. Let me introduce my co-authors, John Noel, Rizvan Kudus, and Ralph Shorts. Why do we talk about phase incompatible bitumen? The chemical composition of binders today is quite different versus binders of the past, where most of the specification systems were developed. Today we have high conversion refineries, which may produce variety of asphalts. We significantly increased recycling of asphalt pavements. For example, in the United States, recycled asphalt pavement consists 20% of any new mix on average. We also use a lot of performance additives, ranging from polymers to improve rheological properties, to anti-strip agents, to H2S scavengers, or warmix additives. And today we are also talking about new materials. Those could be materials from biocomponents, bio-oils, byproducts from bioethanol production. It could be nanomaterials, it can be any new chemistry coming into the market. So the chemical composition is changing significantly from plain vacuum to a residue produced in the refinery. We are aware of these changes, and we also, here in North America, see premature failures of the pavements, fast aging of those bitumen in the field, accelerated fatigue, and low temperature cracking. So any chemical changes to the system may destabilize the system, increase how asphalt or change how asphalt respond to oxidative aging, may impact colloidal stability, and other properties such as physical hardening. So we decided to look whether in existing specification, in this case in North American SuperPave, if there is a way to screen some of those blended bitumen which may not have appropriate performance in the field from more traditional bitumen. We look into this diagram called black diagram, where we plot complex modulus versus phase angle. And this is very unique plot we can use in rheology to track bitumen DNA. What really matters on this plot is chemical makeup. Viscosity is not important here. Let me illustrate that. We have two straight run bitumen here in light and dark blue, 350 penetration and a harder one at 75 penetration. You can see they have identical curve. The reason is they originate from the same crude oil, and they have the same asphaltenes and resins, which are the most responsible for rheological properties. Yet the viscosity is quite different. So how do we alter chemistry? The simple way is to oxidize asphalt. This will change the molecular makeup, how molecules cooperate with each other, the polarity, and so on and so forth. And you can see the black diagram changes significantly with oxidation. So we can track now oxidation by a simple measure. We can say, how is the phase angle at a constant modulus changing? And you can see, you can very easily distinguish all these different binders, which will have very different relaxation properties, failure properties, and so on and so forth. So we could do that in SuperPave, and you can actually calculate phase angle at a constant modulus from existing SuperPave data. All these components are already measured, and we can simply calculate the phase angle at a given complex modulus. So we have done that and plot this phase angle versus a parameter we coined accumulated solids. We know the more solid phase or separate discrete phase we have in bitumen, the poorer the relaxation properties will be, and the more failures we can anticipate in the field. Historically, we know paraffinic wax is not good, creating separate crystals. High amounts of N-heptane insolubles or NHI or asphaltenes is also not good because they can aggregate to bigger entities, and if you have very high amounts of NHI, separate phases may occur. We can show that phase angle can track or reduce actually with increased amount of these solid phases. So can the reduction in relaxation represented by phase angle correlates well to chemical composition. We took this correlation between rheology and chemistry to the next level in our most recent publication presented at Canadian Technical Asphalt Association last November. And there we find correlation between phase angle and also colloidal instability index. In other words, the less colloidally stable the bitumen is, the lower the phase angle. And again, that goes back to those solid interfaces which impeding the relaxation and which chemistry can give us some answer for. The SARA data today can be developed by a modern method called SARA-AD. It's an instrument and method developed by Western Research Institute. I would like to acknowledge. Aging rate is also related to phase angle. In many specifications, we limit viscosity ratio at 3 because we do not want to have bitumen which age very rapidly. Phase angle can do that in terms of superbase specification where such quantity is not represented. So if you limit phase angle at some reasonable minimum limit, then we can also exclude fast aging bitumen. So how this is going to work practically? It is a common practice, especially with high recycling rates in the industry, that a softer binder needed in those pavements is not available in the orbit. So one option industry can do is to use a current binder, let's say PG6422 in this example, and if they want PG6422 in a region where only PG70 is available, they would have to use some paraffinic oil. And let's make this comparison. In a standard superpave, the straight line 6422 and blended with paraffinic oil 6422 will perform adequately and both will pass the specification. When we look at the phase angle though, the picture is drastically different. The straight line asphalt has very high phase angle, very good relaxation at intermediate temperature, while the one blended with paraffinic oil will be probably less colloidally stable and will have much lower phase angle, thus poor relaxation. We partnered with Asphalt Institute and formed a task force to develop this concept further and proposed the 42 minimum limit for intermediate phase angle as a part of superpave specification. We advocated for the change, and American Association of State Highway and Transportation officials agreed to this change and adopted this, and it will be effective July 2021. So let me summarize the key findings. The problem to solve is that we have very different chemistry of asphalts, and which may cause colloidal instability of some of those bitumen, and therefore we needed a parameter to quickly adapt in superpave in order to discriminate those. Phase angle can do this and can do this very effectively. We can use historical data to calculate the phase angle. There is no need for any new testing or validation. We also can use this phase angle to reach the objective of discriminating the colloidally stable and unstable asphalts. And also, we have very low variability in the testing for the phase angle. So that's yet another bonus going with this approach. As I mentioned, the change will be effective July 21, and I will conclude with, let's do more with what we already have. Thank you for your attention.
Let's now move to our next presentation, and let me introduce Gerald Reinke. With more than 50 years experience in bitumen, I'm quite sure that bitumen is part of Gerald's DNA. He had a long and successful career in various companies, such as Asphalt Product Company, Core Materials, or Mati Construction. Currently, Gerald still serves Mati Technology and Engineering Services in the US in a semi-retired capacity. Gerald is also a member of several technical associations related to bitumen technology and performance. Today, Gerald will bring us through a study he did on the use of plant-derived sterols as edge retarding additive.
I wish to express my thanks to the E&E Congress for providing the opportunity to present our research. I also want to acknowledge the other researchers and authors of this paper, Dr. Gillen Baumgartner, Dr. Andrew Hans, and Dr. Seth King. I also want to point out at the start that you may not have time to fully digest all the information on each slide, but you will receive a PDF version of the slides and can examine them in detail if you so desire. My email is posted on the final slide if you want to contact me. If you work in the asphalt paving or bitumen industry, you are acutely aware of the incentives to find rejuvenating additives for aged bitumen that will enable the use of higher levels of RAP, generally greater than 30% RAP binder replacement, and make the use of reclaimed asphalt shingles viable. Both bio-derived oils to serve this purpose have proliferated in the market, and these oils serve to soften aged bitumen. However, some studies have shown that blends of bio-oil treated bitumen products have aging issues. Some references are shown at the bottom of this slide. With this presentation and our paper, we compare aging rates of several bio-oils and sterol blended materials with a lab-produced surrogate RAP binder followed by extended aging through 3 20-hour PAV aging cycles. We have not evaluated every bio-oil on the market. There are just too many, but the results reported in this current work are consistent with results obtained in our laboratory for an additional 4 bio-oils whose data has not made it into the paper. In contrast to the bio-oil data, we will show that sterols, when blended into the same surrogate RAP, age at a slower rate when aged in the same manner. Sterols or phytosterols are plant-derived from seed oils, oils from other plant sources such as corn or soybean, or tall oil, a byproduct of the kraft pulping process. Typically, these oils in crude form contain low amounts of sterol, generally in the range of 1 to 3% or 4% maximum. There is a functional difference between the behavior of bio-derived rejuvenating oils and sterol. Bio-oils that we have so far evaluated are what I characterize as translational in function. Bio-oils soften aged bitumen but do not improve the aging rate behavior of the final blend. Black space plots show no evidence of improvement in G star versus phase angle, only a softening effect. Sterol additives, however, are transformative in function because they alter the internal structure of the bitumen by changing the aging rate behavior between the chemistry of the bitumen, as evidenced by asphaltenes and carbonyls, and the physical or rheological properties of the bitumen, as evidenced by high and low temperature aging results and the rheological index. Black space plots show a change in G star versus phase angle, resulting in a transformed bitumen that is decidedly different from the original bitumen. This black space plot is a comparison between 5 and 10% of a bio-oil material, we have code name Zeta, blended into an aged bitumen, and 5 and 10% sterol blended into the same aged bitumen. You can see here that as the bio-oil concentration increases from 5% to 10%, that the material is softened, as evidenced by the extension of the G star to lower modulus values and higher phase angles. On the other hand, blending the sterol into the same aged material results in a totally different position in black space, showing that the material has been transformed into a different bitumen entirely. That is the functional difference between a bio-oil material and a sterol material. Consistent with the transformative aspects of sterol, the iatroscan data in the current slide provides evidence that sterol is not consumed or otherwise altered during the aging of the bitumen. A sample of bitumen with 12% sterol was PAV aged for 60 hours, and its iatroscan data, the blue data trace here, was compared to a sample of 60-hour aged bitumen to which 12% sterol had been post-added, the red data trace. The sterol areas show as an initial peak prior to the resin peak of the iatroscan data trace. The areas for the 2 sterol peaks are identical before, with the sterol that's been pre-added and the sterol that's been post-added. The areas are shown here. You can see they're nearly identical. The asphaltenes are slightly different. This is an indication that the sterol was not consumed during the aging process of the bitumen. Additional data in the annex provides additional support for this conclusion. The physical properties of the surrogate wrap are shown here, and I'm not going to go through the specifics. The final material was a 117, -18 PG grade, and the low temperature properties were determined using the 4mm DSR. 7 sterile blends ranging from 0 to 12.5% were added to the aged material shown in the previous slide. The data shows that for each sterile level greater than 0.5%, the initial asphaltenes are reduced or decreased compared to a lower amount compared to the original sterile level of the aged material. As the samples are aged through 3 successive 20-hour PAV aging cycles, moving in this direction, the asphaltenes increase, but at a constant and unique aging slope for each sterile concentration. This is further evidence that the addition of sterile yields a final bitumen that is different from the original bitumen into which the sterile has been added. As the sterile levels increase, R values decrease. As R values, this is significant because R value is a rheological based parameter and asphaltenes are a chemically based parameter, and both show benefits from the presence of sterol. There's much information in this slide, but the main point I want to make is that by combining sterol with an aged bitumen treated with softening bio-oil, the sterol can alter or transform the bio-oil blended material into an improved material compared to the original bio-oil material. This is the 10%, the 5% aging slopes are nearly identical to the aging slope of the aged material to begin with, whereas the material with 2.5% sterol or bio-oil plus sterol has a different unique aging slope, which is lower than the aging slopes of the bio-oils by themselves. I'm going to skip this slide in the interest of time, but the information shown in the sidebar here should provide enough data for you to understand what is going on in this slide. In summary, the sterols disrupt or retard the growth of asphaltenes, which is shown in the presentation, and carbonyls, which are shown in the paper. While asphaltenes and carbonyls increase in sterol during bitumen aging, their rate of increase is reduced compared to the same base bitumen blended with equivalent dosage levels of bio-oil rejuvenators we have studied. And finally, reduced asphaltenes and carbonyls in sterol treated bitumen after aging can be correlated to lower R values, reduced high temperature PG grades, and lower T sub M critical PG grades. Thank you for your attention, and I'll take questions if there's time.
Thank you, Gerald. For the final presentation, I would like to introduce Shahin Eskandarsefat. Shahin is currently a senior researcher at Iterchimica in Italy. He received his PhD in civil engineering from the University of Bologna in 2019. During the past decade, his work has focused on investigating and developing sustainable road pavement solutions. In that capacity, Shahin has authored several peer-reviewed articles on asphalt pavement materials and managements. In his presentation, Shahin will present the different technologies he used to be able to differentiate softening agents from rejuvenating agents.
Good afternoon, everyone. I'm Shahin Eskandarsefat, a senior researcher at Iterchimica SRL, and I'm going to present a paper entitled Towards Advances in Differentiating Recycling Agents, Softening Agents vs. Rejuvenating Agents. This research was a collaboration between University of Calabria and Iterchimica SRL with the main goal of differentiating softening agents and rejuvenating agents. So recycling agents can be divided into two main groups of softeners and rejuvenators. Softeners are those of recycling agents that are capable of modifying the rheological and physical properties of an aged bituminous binder, and rejuvenating agents are that of recycling agents that are capable of not only improving or modifying the rheological and physical properties, but also restoring some of the chemical structure of an aged bituminous binder. In fact, this is needed to guarantee the durability of any mixture containing recycled asphalt. In this study, 50-70 pen bituminous binder was used as virgin reference bituminous binder. The bitumen was aged by means of RTFO and PAV, representing short-term and long-term aging, and 7 different recycling agents were used in this study anonymously in 3 different concentrations of 2, 4, and 6% on the weight of the aged bituminous binder. The experimental plan of this study was started by means of bitumen conventional test. And here the table shows the penetration, softening point, and viscosity of the tested bituminous sample. And according to the obtained values, it can be seen that all of the tested recycling agents of this study could improve the rheological properties of the aged bituminous binder. The rheological study of this research work continued by means of dynamic shear rheometer. Here the figures represent the temperature sweep test results, and it should be noted that the lighter color in each figure shows the lower concentration, and the darker color represents the higher concentration. And according to the figure, you can see that how the presence of the recycling agents, all of the 7 studied recycling agents, could improve the rheological performance. The study were then continued by means of microscopic analysis. Atomic force microscopy were used in this study. Basically, during the atomic force microscopy, 2 different images can be obtained, consisted of topography images and phase images. And regarding the bituminous binders, usually 4 different phases can be detected, consisted of katana phase or B structures, paraphase, periphase, and sulphase. The image on the right shows how the chemical phases and structure of the virgin bituminous binder is changed after aging and is restored after using the correct dosage of a correct recycling agents. In this case, it can be said that a rejuvenating agent. These figures are the AFM topography images of the study. Here it can be seen that while the presence of some of the studied recycling agents could improve somehow the chemical structure of the aged bituminous binder, some others like number 4 or number 5 destroyed or worsened the condition. The chemical investigation of the study were then continued by means of Fourier transfer infrared spectroscopy. Here the spectra below shows the obtained spectra for the virgin bituminous binder and the aged bituminous binder of this study. And by comparing the peaks and the chemical indexes, you can easily understand how the chemical structure is changed after long-term aging. The table here represents the obtained peak values of the tested recycling, tested bituminous samples containing recycling agents. And in the bottom, you can see how the status is changed after the addition of the recycling agents. Nevertheless, it should be noted that at least in this study, the FTIR analysis were not analysis results were not consistent with our other obtained testing results. Finally, the X-ray diffraction was used for completing our investigation. XRD generally is used for characterizing the crystallite and diffraction specifications of the material. The figure on the top shows how the obtained band of a virgin bituminous binder, the black one is changed after aging, the red one. And the figure on the bottom shows how the addition of 2% and 6% of the recycling agents could improve the characteristics of the band. And the table on the right summarizes the overall characteristics of the tested bituminous binder. Here, the figures are related to the obtained bituminous binder, the band of the obtained bituminous binder during XRD investigations. Accordingly, same to other testing methods, it can be seen that the presence of some of the recycling agents could improve the characteristics of the band, the presence of others worsened the characteristics, or even in some cases resulted in the presence of a new band. Conclusions. In this study, conventional testing methods were found necessary, but of course not sufficient for investigating the performance of recycling agents. DSR analysis could provide a wide knowledge on the rheological and physical properties of the samples containing recycling agents. It was shown that while increasing the concentration of the recycling agents could decrease the stiffness at high temperature, the same may not be attained at low and or medium temperatures. Despite the fact that FTIR analysis of this study provided useful data on the aging mechanism from the chemical point of view, however, the overall results were not consistent and in line with other testing data, tested and they obtained data. At least in this study, it should be mentioned. In conclusion, DSR, AFM, and XRD were found useful tools for investigating the chemical structure of the aged bituminous binder in presence of the tested recycling agents. The methods are suggested for differentiating the rejuvenating agents from those of softening agents, where both of them still can be considered as recycling agents. However, just rejuvenating agents could guarantee the durability of any asphalt mixture containing reclaimed asphalt. Thank you for your attention, and join us to save our environment.
Thank you, Shaheen. So now comes the last questions and answer sessions. So as for the first session, we will have 10 minutes to cover the question you already posted. If you did not post any question yet, feel free to do so now. So let's start with the first question, which will be for Gerald. Gerald, would you expect the inclusion of sterol into virgin bitumen to reduce the aging rate?
Our data shows that it decreases the aging rate compared to the control material, compared to a lot of other bio-oil materials that we've looked at.
Clear answer. Thank you very much. Next question will be for Pavel. Pavel, is there a critical colloidal instability index value in terms of binder mechanical performance?
That's a difficult question to answer, but we set the limit for phase angle in the specification at minimum 42. So from the data we have, you can kind of interpolate, but it's not, of course, perfect fit between rheology and chemistry. So it would be in the vicinity of 0.45 to 0.5, but I would not certainly recommend using this as a sharp specification or limit. You know, it's more to get some orientation to the problem here.
Great. Thank you, Pavel. The next question will be for Shaheen. Shaheen, how do you interpret the AFM images in respect of the B structure and in relation to the performance of the bitumen? Do you consider this to be only surface phenomena and therefore a change in surface properties, or do you believe that this affects the bulk material also?
Oh, well, this is very complex question. Honestly, I would say that well, we have done this AFM analysis in different dosage of using different dosage of recycling agents, and almost in all of them, by comparing the different phases, as I said, 4 phases, well-known phases of the bitumen, we could easily see that how these phases are changing by addition or reduction or increasing the amount of rejuvenator. But just I would like to clarify something in this here, that the target was not analyzing the effect of the rejuvenator, but we're qualifying the methodologies that can be used to differentiate the softening agent from rejuvenating agents. Actually, and this was the reason that at this stage the material were used anonymously at the recycling. I called them recycling agents, and I didn't try to. We haven't tried to differentiate them and saying them which of them are rejuvenating agents or which of them are softeners. So the target was not how the material affects or change, but the problem we were trying to finding out among the existing methods, existing apparatus that we have in our laboratories, how we can use them in the let's say in a simple way to differentiate these additives. And all of us we can as the first slide I showed that all of these 7 additives that have been used showed this very similar results when you consider the just the physical properties. So maybe it's not reliable for the durability of the mixture you are going to produce with reclaimed asphalt.
Okay, thank you, Shane. The next question will be for you, Gerald. In fact, there is 2 questions in one. The first question is, what is the effect on low temperature cracking resistance of addition of sterol?
The main benefit of the sterol is that it modifies the M value more than it modifies the S value, so that you get a reduction in the M critical temperature. It reduces the M critical temperature when you add sterol to the binder. So that's going to be related to the cracking value of the binder, of the bitumen.
Clear, thank you. And the second part of the question was, does the addition of sterol reduce the negative effect of adding more wrap on cracking resistance?
That's the reason why we use the lab aged material, what I call the surrogate wrap, because it shows that you put the sterol into this, again, lab aged material that is similar to a wrap, and it reduces the M value, it reduces the high temperature stiffness properties. So what it's going to do when you add it into a wrap mix, it's going to reduce the impact of the wrap properties in the final blend. In fact, we've got two test projects on pavements right now that are in their 3rd year of performance in the field, and that's what we're seeing. Those jobs were all done with wrap.
Okay. Thank you for your answer, Gerald. The next question will be for Pavel. Pavel, do you know if a phase angle limit has already been used as a purchase specification by some companies?
It will be. The change in AASHTO, which is the governing body in the United States for bitumen purchase specification, is going to change in July. So for any bitumen supply to the market where your G-star sign delta value for the intermediate temperature exceeds 5,000, the phase angle, if it's above 42, will allow that asphalt to be accepted in the marketplace. So not right now, but it will be in about a month from now.
Okay, clear. Thank you. The following question will be for Shaheen. Do you think the rejuvenators are undergoing a chemical reaction with the bitumen fraction, and which one?
Very good. It's almost continued the first question, how impacts the parameters of the bitumen. So I will use this opportunity also to continue to answer the first question. Actually, regardless of whatever it has been tested, either rejuvenator or softener, we could very easily see that, especially during the AFM analysis, we could see that how the addition of these recycling agents could change the properties of catanophase or BS structures, and also periphase. I'm not honestly referring to what these phases what refers to which sort of fraction. They are some researchers or scientists believe that these catanophase or BS structures are asphaltene, some other not. They believe that they are waxes or paraffins. Whatever it is, regardless of this issue, it was, and I do believe that rejuvenator impacts the chemical structure, and at least in the several studies that we have done, or personally I have followed, I saw very clearly, even in this research, still I don't know which one were rejuvenator, but I could see that some of the additives destroyed the chemical structure, and also during the XRD diffraction. I'm not very expert in this method, but our colleagues in this research also found out the same performance during their analysis and their spectra, they obtained spectra. So I do believe that rejuvenators have a great impact on the chemical properties of the bitumen, and I highly suggest to our colleagues to do not believe just the physical properties, and in the worst case the traditional ones, but anyhow I do believe that we should follow some more deeper analysis if we would like to guarantee our mixtures, which every day now we have increasing amount of recurrent asphalt in our mixes, especially in Europe, you know very well. So yeah, I do believe that it has a great impact.
Great, thank you, Shaheen.
Sure.
The following question will be for you, Gerald. Which bio oil are the richer in sterol, and do you have any recommendation?
Most bio oils have very little sterol in them. It's only in most cases there's no sterol. There's no sterol because they're refined to remove all but the carboxylic materials, the fatty acids or the fatty esters. So at best you're going to have 1% or 2% sterol, and generally you will have no sterol in the bio oils.
Clear. So that's a very clear answer. Thank you, Gerald. Next question will be for Shaheen. Shaheen, did you confirm your findings by doing tests on asphalt mix also?
Yeah, well, very good question. This was the first stage of our research, and it was for 2 years ago we prepared this paper. But I'm pleased to inform you that yes, we have done to confirm our and get a comprehensive conclusion from our work. We have repeated these methods with using different additives, and also and tested both in the same binder scale method and also asphalt concrete method. And yes, we have done this with again together with our other researchers and scientists in the University of Calabria and other institutes. You will find a paper regarding this. If you find out the name of the authors of this paper, you will find some more recent papers representing some more earlier results here. We have done both binder scale and some mixer scale tests, and we can confirm that these methods were reliable at this stage. Yeah.
Great, thank you, Shane. I will have a last question for Pavel. Pavel, is a phase angle control another method of limiting the R value or the delta TC, since we can show that these are all related?
Yes, they are related, and they ultimately lead to very similar phenomenon or mechanism. So that we show there is a relatively robust correlation between phase angle at a constant modulus and delta TC, for instance, right? I think that a phase angle is a little bit more elegant because it goes to basic rheology and doesn't rely on artificial limits. We put for M value of 0.3 and stiffness at 300 megapascals. But other than that, you can also think that any testing at low temperature is difficult because you get into realms of physical hardening and the material evolves in time to all these processes there. So the testing at low temperature is a little bit less reliable. It can be sometimes fairly far from thermodynamic equilibrium. So testing at intermediate temperature is faster, easier, and probably more accurate.
Great, thank you, Pavel. So here is the end of the session. So I would like first to thank again all the presenters of today. It was really great presentation and a very, very nice Q&A sessions. I'm sure all of us have learned a lot today. I would like also to thank you all for your attendance. I hope that you really learn things as well. And if you've got any additional questions, please feel free to join a presenter in the auditorium. So I wish you a great evening and hope to be able to meet you all for real, I hope, really, in the coming future. Thank you. Bye.